Everybody, it is Jono from Seneca, and today for your A-level chemistry revision, I am going to be going over Le Chatelier's principle. Now, if that intro sounded a bit more dynamic than normal, it was intentional because we are talking about dynamic equilibria, really important factor of Le Chatelier's principle. Now, I never learned French, so I might be saying Le Chatelier wrong, but it doesn't matter. As long as you know how to spell it, honey, you're good. There's no oral exam in chemistry. Le Chatelier, how do we spell that? L-E space C-H-A-T-E-L-I-E-R. Right, let's go. Dynamic equilibrium. If a reversible reaction happens in a closed system, a dynamic equilibrium will eventually be released. A closed system is a system where reactants and products can neither be added or removed. Dynamic equilibrium. At dynamic equilibrium, the rate of the forward reaction equals the rate of the backwards reaction. The equilibrium is dynamic because both the forward and backward reactions are still taking place. So the key word we use to describe a chemical equilibrium is dynamic. And what kind of system does the reaction need to be in? It is a closed system. Closed, no more orders like do not pass go, do not collect $200. Nothing's getting in, nothing's getting out. That system is closed. And remember, at equilibrium, both the forward and backward reactions can still happen, but the concentrations of the reactants and products remain constant. So the reactions are still happening, but the concentrations of the reactants and products don't change. So we describe the equilibrium as dynamic because it's moving, it's peppy, it's having a good time. Le Chatelier's principle. Now, this is a powerful tool for predicting the effect of physical changes on the equilibrium. So, Le Chatelier's principle is simple but powerful. And it states that when a change is imposed on an equilibrium, the equilibrium position will shift to oppose the change. What are the changes? So, it could be a change in temperature, pressure, or concentration. Equilibrium position. The equilibrium position describes how much of each chemical you have. So if you have 50% reactions and 50% products, that's one position. But if you have 75% reactions and 25% products, then the equilibrium is in a different position. Easy. So how do we use Le Chatelier's principle in practice? If you change a system by heating it, increasing the pressure, or changing the concentration of a reactant, the proportion of reactants and products will change to reduce the temperature, reduce the pressure, and change the concentration of a reactant. Le Chatelier does not like change. It likes stability. It likes to keep everything chill and 100%. So it doesn't want anything to change. So with Le Chatelier's principle, the system will respond to reverse any changes placed on the system. So like in this example, if we heat up a system, Le Chatelier's principle states that the system will respond by reducing the temperature. If we increase the pressure, the system will reduce the pressure, etc., etc. So let's go through an example to hopefully consolidate that because it can be a little bit complicated. Let's say we have a reversible reaction and the forward reaction is exothermic. And if you remember, exothermic reactions give out heat. Make sure you check out the episodes on kinetics and energetics if you need to get back up to speed on enthalpy changes and what exothermic reactions are. But let's just say you've checked out those episodes and you're a pro on enthalpy changes and you know that exothermic reactions give out heat. So let's say we cool this reaction down, like maybe we submerge it in an ice bath. The equilibrium position is going to shift to the right, i.e. the forward reaction is going to increase. This will counteract the change and return the temperature of the system back towards its original value. And this is going to increase the proportion of products relative to reactants. So that was a good illustration how the equilibrium position will shift to oppose the effects of any change placed on the system. So remind me, what is Le Chatelier's principle? You need to be able to define it. It's a fair game for a definition question on the exam. And when a change is imposed on a system, in a system that's at equilibrium, the equilibrium position will shift to oppose the change. So let's just consolidate this by running through an example. So what happens when an exothermic reversible reaction is cooled down? So in an exothermic reversible reaction, the forward reaction is going to be releasing heat. So if we cool down the system, we want more heat, so the rate of the forward reaction will increase, so the equilibrium will shift to the right because more products will be formed. So that's how we can decide what is going to be happening to a system at equilibrium using Le Chatelier's principle. Let's talk about industry and yield next. One of the most important places to understand equilibria is in industry. Catalysts. So far we've talked about heat, pressure and concentration. So what about catalysts? They're feeling a little bit left out. Now, catalysts have no effect on the position of equilibrium. All a catalyst does is speed up the rate of the forward and backward reaction equally. Any reaction will be faster if you heat it up. So far so good. But exothermic reactions will have a lower yield when the temperature is increased. Because a number of useful reversible reactions are exothermic, it is important that we find compromises between reaction rates and yields. A good example of this is ethanol production. Ethanol is produced in an exothermic reaction between steam and ethene. The conditions used are 300 degrees Celsius and 65 atmospheres of pressure. Phosphoric acid is used as the catalyst. At lower temperatures, we would have a better yield, but it would take longer. So 300 degrees Celsius is the compromised temperature. A higher pressure would give a better yield, but it's very expensive to create and maintain high pressures. So 65 atmospheres is the compromise pressure. So that's an example of how compromise can be important in industry when considering equilibrium and reaction rates. So thank you for joining me on this revision episode for A-level chemistry. I've been Jono from Seneca. Keep up all your hard work and well done for being proactive in your learning and taking the time to listen to this episode. Look forward to joining you on the next one. Thanks for joining on this one.